Hello and welcome to Disseminate, the computer science research podcast. I'm your host, Jack Wardby. I'm delighted to say I'm joined today by Per Fuchs, who will be talking about his VLDB 22 paper, Sortledton, a universal transactional graph data structure. And I believe this was, you can correct me if I'm wrong here, Per, but this was nominated for best paper, right? So
it's a run-up, yeah.
Fantastic. So Per was a PhD student at the Technical University of Munich, and he's now working at Tableau. And his research interests are graph database systems and dynamic graphs. So welcome to the show, Per.
Yeah, thanks a lot for the introduction. I'm happy to be here.
Fantastic. So can we start off by explaining to the listener what a graph database system is, what graph processing is, and just sort of give us some background to the paper?
Yeah, so basically for me, graph processing or graph database systems are really around handling at least 3 different graph workloads. These are graph pattern matching, analytics, that would be PageRank, and traversals like single source shortest path. And all of these have really different requirements to watch the system, different access patterns to what the underlying data structure, which is where this comes into connection to my work. For me, it's really important to say it's universal. You need to have all 3 of these workloads. Otherwise, nobody wants a system for one workload, this system, and then another system in his, for his company to support the second workload, and then this third one maybe for the third workload. And as well, you want updates on the systems. You don't want to reload the graph every time. It takes longer to reload a graph than to run PageRank. So a lot of the static graph processing systems out there are a bit, it's difficult to put them into industry, I would say, yeah. So there's a connection to what can we really use in industry here.
Fantastic. So just kind of, I guess, going back a little bit, how did you get interested in graphs in the first place? What was the attraction here?
I started really early. My bachelor thesis was already connected to graph database systems. My supervisor let me use it to detect denial of service attacks and programs, and so in graphs, which represent programs. And always found them fascinating because they concentrate more on the connection between things. So relational database systems have a lot of entities in them, and then you join them to get results. But graph database systems put like this idea of there's a very important connection between many things as a first world citizen and makes it really easy to express these ideas normally in an interface. So that's another big challenge here, which I didn't touch on in my paper, but I would have liked to in my PhD.
Awesome. So I know in your paper, you say that it's an open problem that building a system that can efficiently process this whole range of graph algorithms over a dynamically changing graph dataset. So it's still an open problem. But so why is this? Can we maybe elaborate on that a little bit more?
Mm-hmm. Yeah, the challenge is really you have different access patterns for each workload. So there's intersections or generally set operations for graph pattern matching, which you need, which requires you to have a sorted data structure on a hash set. You want very, very fast inserts, up to 2 million a second over the whole graph for edges. That's known industry needs of Twitter and Alibaba. And finally, you want this to be really easy to scan because this is what graph analytics, analytics and traversals mostly depend on. And you want this to have random access towards each neighborhood, which is super important for traversals. And each of these things is solved in its own. So there are data structures out there which we can just put together to make a graph data structure. And this was kind of an observation I had really early on. So my feeling was there is a nice and easy solution reusing existing things out there to solve all these challenges in one. And then the next big challenge is to do that with utmost efficiency because in single edge is a super small entity. It's 32 or 64 bytes. So that's just super small and every overhead will show.
Cool. So I guess that segues us nicely into what is Sortledton. And I always struggle to pronounce this. So am I pronouncing it correctly? Because I think when I first read it, I was like, is it Sortledton? Yeah, it was confusing. So how do I pronounce it, I guess? And am I pronouncing it correctly? And what is it, right?
Yeah, it's sorted. It comes from being sorted, sorted. And it's basically a simpleton idea, it's very simple. It's and that's the combination Sortledton in the end. Maybe a bad work joke on my side. I think nobody ever got it.
No, I didn't realize that was it, but no. Cool. Yeah. So I guess what is it? Yeah. So can you give us a high level overview of what it is, and then we can dig into the details.
Yeah. So Sortledton is the data structure which this paper is about, and it's very simple indeed. It's basically a very well implemented adjacency list. So everybody knows the adjacency list, and then you dig into all the requirements I said before, and you can find out that you can reuse existing data structures to build something. And that is Sortledton, a very highly efficient adjacency list. But I think the paper has much more to offer. So the data structure is what's all arranged about. The discussion is all around this data structure. But we touch on each design decision we took for coming up with this data structure in the end. So you can see the trade-off we made, and you can see which trade-offs are there in the process of designing a well-working graph data structure. So my hope is that with this paper, after you read it, you have a much deeper understanding of what it takes to build a data structure. And then you can take Sortledton, which is so simple that it's easy to understand and explain, to build your own data structure on top of that. Because you understood it so well, you will know which parts you would need to change to make it really well working for your specific workload. And it's also, due to its universality, a good base to start with for a graph database system.
You touched on it there, but can we talk a little bit more about what the design goals were when you were developing Sortledton?
The design goals, I think, were on two sides. Once, it should be very dynamic. Mm-hmm. Talking, as I said, 2 million updates per second. We actually made 4 million in the end, and this is fully transactional, serializable updates of single edges. And the second design goal was to be as close as possible to the static gold standard data structures for graphs, so namely the compressed sparse row representation. And we wanted to show how close you could get while being dynamic and transactional. With that, there was a third design goal. I think that should be in every data structure you design. It's space efficiency, right? It should be very space efficient. And these, I think, were the 3 design goals we gave to us, and wanted to press them to the bare minimum of what's possible, and explain why we believe this being the minimum.
I guess my next kind of question is, and I know that the sort of the key idea, and I guess now I know what the idea behind the name is what were the key ideas underpinning Sortledton?
The key ideas underpinning Sortledton is, well, first of all, there are a few principles underpinning it. It's simple, mm-hmm. and it should be explainable. It should reuse existing things, and then it should be a very, very performant solution in the end. So that was a principle we were aiming for. And the key idea to get to that is to analyze the access patterns of each workload, clearly write them down, and then say, we need that. Where did we get that? And find out that there are 5 access patterns in the end. And out of these 5, one turns out to be just very less important than all the others, which it makes it easy to design something in the end. So kicking out the one property, which a lot of people believed in the beginning to be very important for a strong graph data structure. And then it turned out experimentally, it's not that important. You can't get that much from it. And then by removing that, you can show that an adjacency list is basically as strong as a CSR, and that makes it so much simpler.
Cool. So can you maybe go through these 5 things and these 5 properties and talk about how, because I know you did some sort of like initial experiments, micro benchmarks to explore the different space here. Can you maybe run through those and talk through your initial sort of methodology for working out what's going to, and arriving at the point of this one that everyone thinks is really important. It's actually not that important.
Mm-hmm. Yeah, sure, I can do that. So basically, CSR has 5 access patterns covered really well. The first one is if you want to go, you have a vertex and you want to find out where the neighborhood is, that's a single indirection lookup. That's the first access pattern or property. I think access pattern is probably the better word here. The second thing is once you have a neighborhood, it's all sequential memory, so you can scan it with the most efficient as you can be with modern hardware. The third thing is that sorted. Each neighborhood is sorted in each other. All vertices are sequential, which is important for some algorithms as well. They want to access all vertices in the same order. And the final fifth access pattern is if you want to access all neighborhoods in the order they are stored. And this is happening a lot with analytics. And this is the only difference, if you think about it, between a CSR and an adjacency list. An adjacency list can cover all the other four with ease, but this one having all the neighborhoods sequentially in memory, that makes the CSR really different from adjacency list. And it's very hard to get right if you want to have it dynamic, because you have this gigantic data structures holding all edges of the graph. And this is just a very hard data structure to get right. There are existing approaches to do that out there, but they get quite complex. And then you can run a simple micro experiment of building the simplest adjacency list you can think of standard vectors and a CSR. And then you compare them across a wide range of workloads. So the Graphalytics benchmark we used, and it shows that there's very, very little difference between a very simple adjacency list and a CSR. The difference is 1.1 or 1.2x in performance, so meaning latency of all the workloads. And yeah, by this experiment, you can just say, okay, we leave this one property out, and then we build an adjacency list, which is a bit more complex than the one we just used, and we can expect very good results. To give a little context here, more context here is, we also ran micro experiments for each of the other access patterns. The next most important access pattern here would be a slowdown of 3x over all the workloads. So one can clearly see that there's a huge difference between the importance of these access patterns. And the most important access patterns in this benchmark and the micro benchmarks would be actually to be sorted, because you simply can't run graph pattern matching without being at least sorted. Yeah.
Awesome. So you touched on it a little bit there, and that there are other existing data structures out there. How does Sortledton compare with these? And maybe can you give a brief overview of what's out there, and then kind of how you contrast with those?
Yeah, let me run through that. Basically, the other graph data structures we looked at were graph data structures which supported single edge updates. We believe single edge updates to be really important for graph database systems. However, this is something we kind of reconsidered after writing this paper, so we maybe can touch on that later again. So Stinger, Llama, and Graph 1, they can support analytics and traversals quite well, and really recent papers under that. And Stinger is one of the old ones, and Llamas as well, whoever everybody refers back to again and again. Then we have LiveGraph, which added transactional support to the picture. So again, really important for graph database systems. And finally, we have Tiseo, and Tiseo is the only one which has sorted neighborhoods. So it can the only one supporting graph pattern matching so far. Tiseo was only out a year before us on the same conference. And basically, they were finishing up doing while we were writing our paper. And so the main difference to Tiseo is we're much simpler. Tiseo has this last access patterns of the CSR. They have it, but this makes them so complex in design that, yeah, it was nicely to show that you could also do the same or maybe have better performance, which is a simpler system, yeah. So that's the difference here. There's one system we didn't compare to, but I think it's really notable. It's Aspen. And this is something one should have an eye on. We didn't compare to it because it only supports batched updates. But again, as I said, we reconsider this towards the end of our work, I think. And they do really strong work as well.
How did you go about implementing Sortledton? So how was it implemented? How difficult was it to implement? I'm guessing with the fact that it was designed to be simple, it's much simpler to implement than something like Tiseo would be.
Yeah, I would say so. So the implementation is in C++ and from scratch. And it's basically an implementation of a vector for the index, which we actually used from the Intel building blocks. And then we have the implementation of a blocked skip list. So a blocked skip list is a skip list where each node holds multiple elements. Yeah, that's mainly it. And over that, we built transactional support by, we redesigned the transactional support for relational systems, took the paper from our share, and again made this a bit simpler, realizing two things about graph workloads. The first thing is mostly it's very, very small updates, like a single edge or 2 or 3 edges. So updates tend to be very, very small. And second, normally what you want to touch before you do the update. You want to at least 5 edges. That means I need to lock the vertices for each side. So at least most 10 vertices will be touched. So you know the right set before. And by that you can save on, for example, you don't need an undo list then anymore.
Cool. So how did you arrive at that assumption that there is small updates and that the size of them kind of a priori?
Yeah, I mean, it's one of the biggest challenges to actually get real-world graph workloads. We found this very hard. So what we did, we just looked at all the benchmarks which are out there, mainly the SMB benchmark. And we find that the SMB benchmark focuses on this really small updates plus one thing. They have deletions in there, which can be cascading. So there is actually one workload out there which we are aware of, which is not falling into this area of really small updates, cascading deletes. But we also came to the conclusion that cascading deletes is something totally new, which so far no transactional system we are aware of could well. Any transactional protocols we know of wouldn't work so well with something that can basically touch a whole graph, and you have no idea how much of the graph it will touch before. If you want to run this with really read-heavy workloads like PageRank in concurrency, that would be very hard to get right. So we excluded this workload. So this workload is something we couldn't do, and I believe this would be a paper in its own to actually come up with a good transactional support for cascading deletes or other things that can start one vertex and go to the whole graph and then do read and writes on that.
How long was the implementation effort? Are we talking the magnitude of months, weeks, years?
So the implementation effort was maybe around, I think, 2 months. Kind of started in January to March, so roughly around that. And then there was a prolonged thing of actually getting this evaluated. We were really happy. Dean DeLeon from CWI just published Teseo, kind of our main competitor there, and he published a test harness with that. So we could just reuse that. So that was just amazing for us, made it so much easier, and we had great support from him. But however, we had to find out a few bugs or, let's say, consistency issues between our implementation and how he saw things, and until we get the numbers right, such that when we measured on our system, we got the same numbers measuring with his test harness, and this took quite a long while. I think it was maybe another month or two. And we then finally got the numbers we wanted.
Fantastic. So let's talk about the numbers then. So how did you go about evaluating Sortledton, and I guess what were the questions you were trying to answer? So and I guess what did you compare against it as well, right? So there's a few questions here. You can take them one at a time.
Yeah, so throughout the paper, we had a lot of micro benchmarks to just give the meat behind our decisions, right? To be like, this is why we do that. Here you can clearly see why we did this in the micro benchmarks. For this year, I think just read the paper, and then the second one is the evaluation of our paper, of course. And here we touched first on how many updates can we do, throughput per second. And we always compared against all the competitors I named doing related work. So we did throughput per second. We compared how much slower are we and any of the others compared to the static gold standard CSR. We compared how much do we scale up for inserts. And then we looked at HTAP. So what happens if we run the Graphalytics benchmark, extremely read heavy, while inserting as many edges as we still could at the same time. So that's basically combining the two first experiments and then show how much there was a slowdown on either side. And Yeah, that's our experiment. So that's a question we try to answer.
Cool. So
space, of course. We looked at space or efficiency as well. Yeah.
yes. So what was the experimental setup in terms of the hardware and the variety of benchmarks you used?
Mm-hmm. So we basically used one benchmark, which is known, the grapholytics benchmark. And for all systems, we used the same implementation of the algorithms. Mostly they were based on the benchmark suite from Scott Beamer. So the implementation of the algorithms is the same for each data structure. You only see the difference in the data structures there. And the other benchmark is, it's not a clear benchmark. It's simply you take a lot of graphs and you try to insert all the edges as fast as possible. And in our case, I think we inserted 80% of the edges first, and then the last 20, measured the last 20, because it's not that interesting inserting it into an empty graph. So that's that. We covered deletion in a slight variation of this experiment of inserting everything as fast as possible. And the H-stop experiment is really a clear combination of the two before. We ran them at the same time on the same machine. You asked about the machine. We evaluated on an Intel CPU, which I think had 48 physical cores.
So I guess now, what were the key results? What were the headlines? What's the interesting findings from all of these experiments?
Yeah, so how many updates can we support? It's around 4 million, and this is averaged over a wide range of graphs. So the smallest would be Dota League with 50 million edges, super small, because you also need to be fast on small graphs. We found out that at least one competitor wasn't that fast on small graphs. And then on the other hand, you need to be, of course, good on big graphs. And we took the Friendster graph there with slightly over 2 billion edges as our biggest graph. Average on this is relatively stable over all graph sizes. We can have 4 million updates. Said industry needs 2 million, as far as we are aware of. And then the second thing is how fast are we running read-heavy workloads, and we are roughly 85% of CSR. So we are very close to the static data structure here. And finally, we are 2 times as big as the CSR and 2 times as big as more or less the theoretically minimum, because you need to leave some space off for edges to insert, and then you need some space for versions.
Cool. Do you think it's possible to get, so that's like 85% of the CSR. Do you think it is possible to get it closer with some more, or is it theoretically there's a bound there that you're going to rub up against, no matter how good the implementation is or how whatever, you're never going to quite get there?
Yeah, that's a very interesting question. To be honest, I have no clear answer to that. I think we left very many optimizations in our data structure on the way, because towards the end of this paper, we really needed to get it published, because Teseo came out and they were really close to what we wanted to have. And then, we really felt the pressure to put it out there now before somebody comes in front of us. And just in the same time we got ours in submission, Terrace came out. This is in Sigmund, covering quite similar ideas, and also the idea that you can use an adjacency list to have different set implementations depending on the characteristics of the neighborhoods, which was an idea we were probably aiming for as well. So things came out, and then we were pressured to finish up. I forgot the question. What were I going to?
Whether it's possible to close the gap on the CSR.
So perfect. So therefore we left many optimizations out. So there might be 5% to get even in our implementation still. But no, there's no theoretical limit, but there's a limit of something needs to cost, right? There's no free lunch. If you want updates, you won't get to 100%. And the last few percents will be harder and harder. And then it also becomes a question of worthwhile.
Yeah, sure. Diminishing returns there for sure. So Are there any situations in when Sortledton's performance is suboptimal? And I guess this is just kind of getting at what are the general limitations of this data structure?
There are two general limitations I'm aware of. The one is fixable. So we aim for single edge updates. As I said, we believe that to be very important for graph database systems in the beginning of our work. And then later on, when I look back at it, being finished writing it, I was like, yeah, okay, in the end, I didn't find a workload which really needed single edge updates. Many workloads could be done with batch updates. It's basically just a question of freshness in between. And there are papers out there that show you can get really close to the freshness with batched updates as you could do with single edge updates. So looking back at it, what I would have done is batched updates. You can get much higher throughput on updates, make system design of an H-chip system much simpler. And so that's one thing, which I think is a limitation, but it's not so much in the design. We could change the transactional system behind it, and then we could support batch updates on the same data structure. And the second thing is that there's a current trend to going away from in-memory systems towards systems which use SSDs really well. I think Victor Leis is really leading there. A lot of his PhD students have great work towards that. And our data structure is designed for in-memory. And if you want to go off memory with that, you would have a harder path than if you choose TISO, which is the other system I talked about multiple times before. CWI, Dean DeLeon, and Peter Bonks are the authors. Great system, great work. And I think if you wanted to go SSD with it, they have a simpler path towards, but therefore a much more complex in-memory implementation. And there might be a combination of these two where you can get the best of both worlds.
Interesting. That's really interesting. When you were working, did you ever think about doing some form of like a distributed data structure and how that might look like with Sortledton?
Distributed, yeah. So if you wanted a distributed in-memory system, again, I think the Sortledton would do really well because it can so easily be pulled apart. It's an index, and then it points to places where the neighborhood is. So in this regard, I don't see any issue with Sortledton to be pulled apart across multiple systems. But the real challenge between distributed graph processing is, of course, somewhere else. It's about getting the partitioning right? And this is a whole different question, a whole different line of research. And I think it's a very, very hard line of research where I didn't see any results that where I read the paper and were like, that's it. The only result I saw, which was really convincing, is I think from Alibaba, which basically showed that depending on your workload, different partitionings will do you well. And this just makes it harder because they clearly show there's a very clear connection between partitioning and workload. And this makes it very, very hard.
Complete moving target. Yeah. Interesting. That's cool. So Sortledton's publicly available, right? There's a GitHub repo there. You can go and pull it down and have a play with if the listener wishes to.
Yeah, it's publicly available. It's open source. I think, though, the implementation is probably more of a guiding or a proof of concept. So if I would want to use that in an industry system, I would probably re-implement it. And this is very easily done because it's clearly set which data structures are used in each of these data structures, skip list or blocked skip list. And block-free vectors are well known. It's not hard to implement them yourself. You maybe get a much cleaner implementation than a PhD student trying to wrap up a paper and having his first C++ project within a few years. So, yeah.
Cool. So, what's the API like of the data structure? How, if I as the end user of it, how do I interact with it?
I think exactly as you expect. It has insert edge, delete edge for the updates. And then you can ask it to scan neighborhoods for you. And it will basically return you an iterator over the neighborhood, but the iterator is batched. So you don't have to call an operation for each new edge, but you have to call an operation for each batch of edges. This is basically, this is one of two ways of doing it. The other way would be to offer you a scan function and you give a lambda in, which is executed on each edge. But the important thing you need to get right here is don't call a function on every edge. These two things work, and I think they have really similar performance. But if you call a function, so an iterator over every edge, you'll have a huge performance hit. And this is also something at least one competitor got wrong. It's an implementation issue you shouldn't make. Be really think about how you access your edges in the end.
Okay, cool. So just does it support properties, or what's the graph model here? Is it just edges, an undirected graph, or can I have labels and edges? I'm getting at, can I support a label property graph model within this?
It's meant to be a topology data structure, so it's mostly vertices and edges. You support edge properties. You can have as many as you want, and you could make them as big as you want, but if you make them very big, it won't work anymore. So you can have a few small edge properties that will work really well. Vertex properties, we didn't implement them, but basically there would be a vector next to the vertex vector, right? It's kind of a mirroring data structure. And then the last question was labels. Labels are a really interesting thing, right? Really depends how many you have. And if you want to partition a graph totally on your labels, then you could just use sortlet multiple times. So one extreme. And the other idea is to have labels in line with the edges. It's kind of the other extreme. Then you don't have much filtering power over them, but you need to still scan all edges and can filter them out over the labels. But then you can use as many labels as you want, kind of properties become labels. So these are the two extreme of the design space you can look at. And both is kind of supported with Sortledton, but what you maybe want to do is something in between, and this is something you would need to build yourself. And I think best paper here is the A+ index with Semisai Huglu as one of his main authors. I think they have the deepest treatment of labels and properties within graph database systems out there. Very great paper, but it's a static graph data structure.
Cool. So when you were working on Sortledton, what was the most interesting thing that you learned, or maybe also the most unexpected lesson that kind of came out of working on this? Under, I guess, such a high pressure environment as well, when you're racing to publish because it feels like everyone else is publishing the same thing at the same time. Mm-hmm. Yeah.
I think the most unexpected lesson wasn't in the technicalities, it was in paper writing. And I think this is a lesson for every PhD student. In the very beginning of this paper, I had the idea from the beginning and it didn't change much towards the end. And I told this idea to a very well-known professor in the area and said, well, there is no paper left in this area. No way you can publish in this area. It doesn't work anymore. It's full. And it turned out to be a best paper runner-up. So apparently it wasn't full. So I think this is a very interesting lesson for every PhD student. If you have a great idea and you're convinced and you can convince a few other people of it, it might be very well publishable, although some people say it's unpublishable.
Fantastic. That's a great lesson to take. Yeah, awesome. So my next question is, progress in research is very bumpy, right? There's ups and downs. So from the conception of the initial idea for Sortledton to the final publication, what were the things that you tried along the way that failed that maybe your listener would benefit from knowing about, so they don't make the same mistakes, I guess?
Mm-hmm. The only thing that really failed was my attempt to implement this fast serializable multi-version control in a very short amount of time, trying to get it right. It's harder to get it right than one thinks. And then, I changed for a simple implementation, which turned out actually to work super well and being kind of interesting because nobody used it before in terms of graph processing. So that was one thing that didn't play out. I think all the others idea played out. It was just worked really well, actually.
Yeah.
There's maybe one thing also I learned doing writing papers. It's a lot about the story. Like I came up with the idea for Sortledton very early on, and then implemented that, and measured that, and then had the numbers I wanted. And then Tiseo came out, and it became much stronger paper over the terms of its vision. Very, very strong paper by then. So the last part of getting this paper out was really storytelling of explaining why a data structure which is just simpler is still really well worthwhile to read about, although it has some weaknesses compared to Tiseo, it had some strong points compared to Tiseo, but in the end was really similar. And the main difference being it being simpler. And then there was a lot of points to make and telling a very nice different stories about it.
The next question is maybe not as relevant for you now that you've moved on to Tableau, but what's the next step? What's the future research for Sortledton? Where does it go from here?
Yeah, so basically my future research would have been to integrate this in some kind of system to make it a much better graph database system. There are two ways going about this. One way is to integrate it as an index, one-to-many index, basically, into an existing relational system. And I think many people tried that, and I'm aware of at least 2 ongoing research projects on very good shares trying to do that. And I think it's a very worthwhile approach. However, there's one weakness with this approach, I think, is that it kind of treats graphs as a second citizen, right? Like second-class citizen. It's you put it in a relational system and then kind of needs to fit the relational model. And the best would be if you could run SQL on top of it. And yes, you can do PageRank in SQL, but it's kind of not natural. And it gets harder for single source shortest path. So there is a bit of an idea, so of my supervisor, Jana Gesheva, where they say, well, what should you do instead of bringing everything to SQL, like graph processing, machine learning? Yes, you can put it all in a relational system. But what we can also do is use relational techniques to build the system, but break down the operators into smaller parts. So the operators of a relational system is, for example, a join, but you can actually break down a join into much smaller operators and build the join out of that, and then expose these smaller operators, which are like, for example, map, or they could be reduce or filter. You can expose these operators as the interface of the database, and then have a much more natural way of expressing machine learning or graph processing system and relational system workloads in the same system. And I think this is a great chance for graph processing or graph database systems, because it gives us a way to be a first-class citizen in these systems.
Fantastic. So can you maybe tell us a little bit about some of the other research you did?
So mostly I've been looking at this work, of course, and then started looking into how you would use these small operators, they're called sub-operators, for graph workloads, and came up with some initial work of how you can express different graph workloads in a wide range of graph workloads as these sub-operators. So this would have been my next work, kind of like setting up a processing system on top, or an execution layer on top of the graph graph storage I had.
What do you think is the biggest challenge in the graph space at the minute?
And the biggest challenge is integration. All the ideas, all the basic ideas for really strong graph database systems, I think by now are out there. And it's time to pick them up and bundle them in one system and show how they all belong together, how they can work all in one system. And just cover a wide range of workloads with these. And then we convince people that it's worthwhile using and building using the system in industry.
Fantastic. And last question now. what's the one key thing you want the listeners to take away from your research and from this episode?
Now, the one key thing is that once you want to build an in-memory graph processing system, and you want it to be really strong, like nearly as strong as a static data structure and have updates, a very simple and well-implemented adjacency list can do that. And the reason for that is that there are 5 access patterns graph workloads, and one of these 5 is so much less important than all the others. So the only thing that makes a difference between a CSR or a complex data structure and an adjacency list, a much simpler data structure. Yeah.
Fantastic. And so let's end it there. Thank you so much, Per. That was fantastic. If the listeners are more interested to know about Per's work, I'll put links to the paper and everything in the show notes. And we will see you all next time for some more awesome computer science research.